Let's talk about series. On the screen here, you can see our first introductory definition. A series, you might also see the phrasing infinite series, but the infinite part is implied. A series is just an infinite sum of numbers. You can see here 1 + 2 + 3, and then this ellipsis at the end implies that this pattern continues forever. So we're going to add up all of these numbers forever. This is really, really similar to a sequence in the last section. The only difference is that we're adding these up to something instead of just putting a comma between them and having them be an ordered list. Keep that general form hidden for now. So we very frequently are going to see series written in sigma notation, which we haven't seen in a while, but we did see last semester. So for example, here you can see the sum from k = 1 to infinity. So this is just add forever. And the formula that makes each term is 1/k. So this k = 1 at the bottom tells us that 1 is the first number you plug in for k, so you get 1/1. And then now we're adding between, so then we plug in 2, that's 1/2. And then we plug in 3 and 4 and so on. And again, because there's an infinity at the top here, which all our infinite series will have, we just kind of, do the first few terms and then put a ... to imply that the sum continues forever. So what I have hidden under this extra paper here is the general form for a series. We're going to have to use this form mostly in definitions and theorems when we're talking about, just an arbitrary series and rules about it and so on. So in general, we're going to write a sub 1, sub 2, sub 3, etc., just like we did for sequences. So these will refer to the first term, the second term, and so on. If we write this in sigma notation, it would look like this. And then I also have included here the version of it with n as the letter instead of k. I'm going to try to stick to k when it's a series and n when it's a sequence, because they're hard enough to keep track of. But technically, any letter can play this role here. So if we switch the indexing to n instead, we have a n next to the sigma, but it still creates the exact same sum of numbers. All right, so pi is my next example. You may be wondering why. So I wanted to make the point here before we do anything else talking about series. We're actually going to be talking about series for the next couple of weeks. This is the beginning of something big. But I want to talk about the fact that they seem like they all would just add up to infinity, but that's actually not the case. So for example, if we look back at this first series example that I had, 1 + 2 + 3 + 4, etc., this absolutely is going to just sum to infinity. That sum just grows and grows and grows forever. So a lot of them do kind of do what our brains think that they're going to do. But it's entirely possible for an infinite sum of numbers to add up to a finite total. I'm going to hold off on this one. This guy right here is called the harmonic series. That's the name of the series, 1 + 1/2 + 1/3 and so on. That one's going to come up a lot over the next few sections and be a really good example for various things. But as of now, it's extremely unclear whether it would convert your calculation, whether it would add up to something. All right, so to convince you that it is possible, before we have any fancy tricks up our sleeve, I'm going to talk about the number pi. So pi is 3.14159, etc. It's a never-ending decimal, but you can look up online. There's millions and billions of decimal places of this number known. But it is just one number, one real number. So with the right perspective, we can actually see this number as an infinite series. So 3.14, that's 3 plus 0.1 plus 0.04 plus 0.001 and so on. I'm just splitting up each of the pieces into their own number. And then I can write these as fractions even. And we don't have to write as fractions, but we tend to see more fractions than decimals in series. So that's 1/10. This is 4 out of 100. 1 out of 1,000. The next would be 5 out of 10,000, and so on. So the number pi, because it's a never-ending decimal, actually is an infinite series. And we can see these really do add up to whatever this exact number is. So it's possible. Okay, so this leads us to another big definition that I'm kind of hiding for now. Yeah. Okay, so this is the definition for the nth partial sum of a series. So given a series, this is kind of our generic looking series. We're assuming the index starts at 1, although this can change. So given this series, the nth partial sum, which we write as a capital S with an index of 1, is the sum of the first n terms of the series. So essentially S sub n, whatever this subscript number is, sets the upper bound of the sigma notation. So you would add up all the way up until that term and then you stop. So this is a finite sum instead of infinite. There is more to this definition, but before we do that, I want to come back up to my first few examples and see some partial sums. So I'm going to talk about this very first example, 1 plus 2 plus 3. Okay, so S sub n stands for any S sub a number. So the first partial sum of this series is just the first term, which is 1. The second partial sum is the sum of the first 2. 1 plus 2 is 3. The third partial sum is the sum of the first 3 terms. 1 plus 2 plus 3 is 6. And so on. So for example, S sub 10, I'm not actually going to add up all these numbers, but that would be 1 plus 2 plus 3. And we continue that pattern all the way until we hit 10 as the 10th term in the series, and that equals some number. So S sub n is kind of like the generic stand-in for any one of these partial sums. So let's come back down to this definition and we'll get a peek at a little bit more of it. All right, so here we have definitions for the words convergent and divergent in the context of a series instead of a sequence. It pretty much means exactly what it meant for a sequence, but it gets its own definition. So we have a series where A sub k is a term of the series. And then the S sub n's are the partial sums of that series. You can make a sequence out of the partial sums. So we don't want a series of them. We don't want to add those additions together. What we want to do is just list them out. So this is S1, comma, S2, comma, S3, and so on. We just want them as an ordered list. That's all. If that sequence is convergent, which we know means the limit exists, then the series it's associated with, we would also say is convergent. And that limit right there is the actual value of the sum. If the limit of the partial sums doesn't exist in any way, then we would say the series it's associated with is divergent. Let's see some examples, or at least one example. Let's say we're given a formula for the nth partial sum. This doesn't typically happen out in the real world, but it's a nice place to start. So we don't really have enough information to know what the formula is making the terms of your series. But let's pretend that we're told that there's a formula, f sub n equals n over 2n plus 5, that gives the nth partial sum, right? So like the S3 third partial sum is 3 over 2 times 3 plus 5. It's just kind of a shortcut to adding up the first, in this case, 3 terms of this mystery series. Okay, so if we're asked kind of the standard question for this section, which is, does this series converge or diverge? And if it converges, find the value. So converge or diverge. If converge, compute the actual sum. We would say, okay, well, at this point, the only move that we know how to do, right, that we have, is to look at the limit of this sequence of partial sums. So we are going to look at the limit as n approaches infinity of the Sn formula. I'll make this 2 separate steps. So that is n over 2n plus 5. And we're considering this a limit, just like in the sequences section in 11.1. This is one that you can think about either using L'Hopital's rule for the continuous version, dividing top and bottom by power of n, or x if you switched into it, or you can use the shortcut n over 2n sub f. All paths lead to 1/2 here. So for this particular series, its sequence of partial sums is convergent to 1/2. So we would say this series overall is convergent, and it would add up to a total of 1/2. So this first page of the notes here ends with a comment, kind of just a takeaway from this definition. If you're given or can find a formula for the partial sums, you can compute your series or determine if it's convergent or divergent as well as the limit of those partial sums formulas. And this is a very, very big if here. This doesn't happen too often. We'll run into a handful of examples in this particular section that have it. And then after that, getting a formula for the partial sums becomes increasingly difficult. So we turn to other methods instead. But for now, this is our one move. And we're going to build up to a second move. Okay, so this brings us to a theorem. So this theorem says if the series of AKs is convergent, then the limit of the terms of that series would be 0. So the individual terms, as though they were a sequence, those terms go to 0 on their own if the series converges. And this brings us to our first convergence test. This is the first of many that we're going to collect over the next few weeks. It's called the test for divergence. So this test for divergence sort of turns this theorem backwards and says, well, anytime I can recognize that this formula in the sum, if I can recognize this formula doesn't head to 0 as a sequence, then there's no way I could have been convergent. So we can conclude that the series is divergent. So this covers the cases where the limit of these individual terms is some other number, but it also includes all of your DME cases as well. All right, so you can see I have 2 examples ready to go here. So for each of these, we're assuming we're asked just, is this series convergent or divergent? So this first one, this formula right here is the A sub k formula. So I want to consider the limit of those AKs as a sequence. So I'm kind of ignoring the sum temporarily. The limit as k approaches infinity of that formula. Again, you have a couple of different options for computing this. You can do the shortcut k over k. You could divide top and bottom by k, or you could do L'Hopital's rule, but all of those paths should be doable. So this tells me if I had made just a sequence out of these and listed the numbers in order, I would say, yes, this is a convergent sequence. But because this comes out to not 0, the divergence test says the series of these numbers is divergent. So our choice here is that this series is divergent, even though the sequence of terms are convergent. Essentially, what's happening is that if these terms are headed to 1, as you keep adding stuff up, you're sort of doing 1 plus 1 plus 1 plus 1, which is going to grow and grow and grow. My second example here is a little bit trickier on purpose. I switched to using n instead of k, just for the sake of practice. Like I said, I try to use k for series and n for sequences, but we are going to run into examples where that letter changes. I also changed the starting value of n to 10 for absolutely no reason, just to get some variety. This 10 is not going to affect how we answer this question at all. No matter where this starts, this thing is either convergent or divergent. Okay, so again, we are going to use the test for divergence and consider the limit of these guys. Technically, this is an a sub n, since n is the variable. So I'll limit n to infinity and put just that formula in there. This is a weird one. So this limit doesn't exist. Because every time you plug in a different value of n, you get 1 or -1, 1 or -1. So it should be positive and then negative and so on. So it doesn't really go off to one of the infinities. It's a true DNA. So this is also divergent by the test for divergence, because these individual terms don't go to 0. This is a good example to consider also the partial sums. So we already have our answer, but we could have gotten it without using the test for divergence by thinking about the partial sums here. So the first partial sum is just the first term, which is -1 to the 10s. That's positive, or 1 rather. And then after that, like your second partial sum is 1 minus 1, which is 0. And then 1 minus 1 plus 1, that's 1. And then 1 minus 1 plus 1 minus 1 again, and so on. So this sequence of partial sums is 1, 0, 1, 0, 1, 0. That sequence isn't convergent, it's divergent because the limit doesn't exist. So we could have decided it was divergent that way as well. I want to end this video by just pointing out the test for divergence is really helpful, but there's one really important thing it can't do. So this test cannot ever prove that a series is convergent. And that's going to be really important going forward. If you do come across a series where the terms go to 0, such as in our very first or very second example here, these terms go to 0 as a sequence. So the test for divergence just kind of says, well, maybe it's not enough information. And in fact, this is a divergent series and a really, really tricky one.